Hi everyone. This is going to be a lesson for linear algebra on characterizations of invertible matrices. I'll tell you that for this lesson, we are going to follow along pretty closely with the textbook by Lay and McDonald. So I'm going to be referring to section numbers and theorem numbers, maybe even page numbers. I don't know, but we're going to follow along with this book, so you'll want to make sure you've got that ready. Also, there is a handout for this lesson, and by the time you're seeing this, I've got this handout posted in the place where I usually post worksheets for our class. So you'll want to make sure that you have this. This section, this lesson is all about this theorem, so you want to make sure you've got it. All right, so let's go ahead and get started. All right, so characterizations of invertible matrices, and we've got our textbook and we've got our handout, so we're ready to go. Okay, so in the previous lesson, we learned about invertible matrices. We learned how to find them. And in this section, we're going to sort of see why invertible matrices are so important. So let me start by saying in section 2.2, that was the previous lesson, Theorem 5 said, if A is invertible, AX equals B has a unique solution. Now, the theorem actually said a little bit more than just that. I'm just kind of paraphrasing the most important point for us for right now. I believe that this theorem also said specifically what that unique solution is. That solution is X equals A inverse B. But for now, we just know that if a matrix is invertible, then this matrix equation has a unique solution. And that's true for any vector B. And when we covered this in the previous lesson, I think that when we got to this theorem, I kind of stopped and said, this seems important to us because it's starting to show us how a matrix being invertible is related to whether or not a linear system has solutions. Now, let me tell you that this works for any vector B, including the zero vector. You know, we said it works for any vector B, but I'm just highlighting the fact that it also includes the zero vector. So, A being invertible implies that AX equals 0 only has, well, before I finish this sentence, let me tell you where I'm headed with this, okay? Think about the homogeneous equation AX equals 0. We know from previous lessons that this equation, this matrix vector equation, always has at least the trivial solution. The trivial solution would be X equals the zero vector. Okay? This always has at least the trivial solution. Now we're saying if A is invertible, it has a unique solution, which means it only has the trivial solution. Makes sense, right? We know it has the trivial solution. We know that it has a unique solution. Therefore, it only has the trivial solution. That's if A is invertible. Now, this implies many things, including, you know, if AX equals 0 only has the trivial solution, this implies from things we've said in previous lessons that the columns of A span Rn. what was that, back from section 1.3 or 1.4. It also implies that the columns of A are linearly independent. Okay, so think back to definition of linear independence. AX equals 0 only has a trivial solution. Yeah, that means that the columns of A are linearly independent. How about this one? The linear transformation X maps to AX is 1 to 1. We can get all of that from A being invertible. If A is invertible, it implies AX equals 0 only has a trivial solution, and that implies all of these things. So if A is invertible, the linear transformation is 1 to 1. If A is invertible, its columns are linearly independent. If A is invertible, its columns span Rn. All kinds of cool stuff. And this brings us to Theorem 8. I guess I'm writing this a little bit larger than usual because this is important. The invertible matrix theorem. Say it loud. The invertible matrix theorem. All right. I am going to say at this point, we're going to discuss the handout. Before I flip to showing some of the handout on the projector, before I even say what the theorem is, I want to tell you that I think that this theorem is the most important theorem of this course, linear algebra. So highlight it in your notes or whatever, and we're going to show it on the screen in just a moment. But before I do that, I want to tell you that given A, statements A through L are either all true or all false. Now, I'm going to do what I can to show this on the screen, but hopefully you've gotten this handout already as a PDF and you can look at it on your own. Maybe you've printed it out. So, the invertible matrix theorem. I'm going to zoom in on it a little bit from the projector. The invertible matrix theorem. It says, let A be a square n by n matrix. I guess we didn't really need the word square there, huh? If it's n by n, it must be square. Let A be an n by n matrix, then the following statements are equivalent. That is, for a given matrix A, the statements are either all true or all false. There's a lot of statements here. Statements A through L. Here they are. So, if you know that one of these statements is true, you can automatically conclude that all of the rest of them must be true. On the other hand, if you find for some reason that for a given matrix A, one of these things is false, then you automatically know that all of the other things are false. They're either all true or all false. You can't have a mix. Notice that item A is an invertible matrix. In the previous lesson, we talked about how to check whether or not a matrix is invertible. We still have a little bit more to discuss on that regard, actually. we learned how to find the inverse. We talked a lot about the 2 by 2 case, and then we also did a 3 by 3 example at the end. There's still some more information to come in future lessons about ways to quickly tell if a matrix is invertible. But anyway, if you find out whether or not the matrix is invertible, if you find that yes, the matrix is invertible, maybe it's a 2 by 2 matrix and you simply check its determinant. That would be quick. As soon as you know that it's invertible, you automatically know all of these other things are true. For example, if I gave you some matrix A and I asked, is the linear transformation 1-to-1? A quick way to check to see if the matrix is invertible. What else? Let's just go through each one. So A being invertible, I think that that's listed first because that's something that is very important to us, and it's something that we can kind of check as a yes or a no. We find out if it's invertible. B says A is row equivalent to the n by n identity matrix. Row equivalent means it's equivalent in the sense of row reduction, that it can be row reduced through Gauss-Jordan elimination to become the identity matrix. Okay. Item C says A has n pivot positions. That seems to make sense, that if you can row reduce it to the identity matrix, then it makes sense that there are n pivot positions, one for each row. The equation AX equals 0 only has a trivial solution. We talked about that one a few minutes ago. The next one says the columns of A form a linearly independent set. I mentioned that a few minutes ago also. But remember, it works in all directions. Like if you know that you have a linearly independent set, then you automatically know A is invertible. On the other hand, if you have a set of column vectors and you know that they are linearly dependent, maybe because of some shortcuts or theorems we said back in that section on linear independence, if you find that the set of vectors is linearly dependent, that means that item E is false, and that means that all of these items are false for that matrix A. So you see how knowing one thing, it seems like it can tell you about something that's completely unrelated. All right, you find that a set is linearly dependent, and that automatically tells you the matrix is not invertible. It doesn't have n pivot positions. Tells you things about the linear transformation. Well, it turns out that all these things are related, even if they might not seem like it at first. Let's see, where were we? So the linear transformation being 1-to-1, I mentioned that a few minutes ago. The equation AX equals B has at least one solution for each B in Rn. All right, if that's true, if there's at least one solution for each B. The columns of A span Rn. I think G and H both look familiar. They both look like they came from something we talked about in chapter 1. So we're going to talk about the proof of this theorem and see where G and H came from. The linear transformation X maps to AX. It maps Rn onto Rn. Remember the definition of onto? So this map is onto. There is an n by n matrix C such that CA equals I, and there is an n by n matrix D such that AD equals I. We'll talk about those a little bit as we go through the proof. And finally, A transpose is invertible. I think that we might have said in the previous lesson, we might have said that item A implies item L. I think we might have said that already. All right, so we're going to remove this from the screen and go back to writing notes, but we are going to refer to this as needed. Let's zoom back out. So here's where we were. Now, you may have seen theorems like this in math classes before that say, here's a bunch of statements and the following are equivalent. Like the following statements are equivalent, meaning they're all true or they're all false. But this is probably the longest theorem of this type that you've seen. I would guess it has a lot of statements that are all logically equivalent. Well, guess what? I said that this was the most important theorem of the semester. Part of the reason why this theorem is so important, it's not just for these statements. It's actually because throughout the semester, we're going to come back to this theorem and add even more statements to it. The list is going to grow even longer. A through L, we're going to start going through more letters of the alphabet. We'll see. We're going to go pretty deep into the alphabet, making this a very big list of linear algebra statements that are all logically equivalent. So they're all true at the same time or all false at the same time for a matrix A. And this section is called Characterizations of Invertible Matrices. And the idea is that we think of whether a matrix is invertible or not has all of these big consequences. And it's almost like every matrix or every linear transformation, can fit into one of these two categories. It's either the type of matrix where everything in this theorem is true, or it's the type of matrix where everything in this theorem is false. Now, I'd like us to prove this theorem, but, it's a very long proof. So what we're going to do is kind of go over, we're going to leave out a few things here and there, but we'll get everything we need to understand why this works. Now, before we even start proving it, let me talk about the strategy. How would you even prove something like this? There's so many statements. Now, do we need to prove that if A is true, then B is true? If A is true, then C is true? If A is true, then D is true? Like, think of how many combinations there would be. I is true if and only if F is true. G is true if and only if K is true. Like, there's so many, and they would all be if and only if. So it would take forever if we did that. There's so many combinations. Technically, we could do that, though. We could try to prove item A implies the other 11 statements. We would then show that item B implies the other 11 statements. Etc. What would we have? 121 little proofs to write? We're not going to do it that way. Instead, the way that we're going to prove it is something that I'm going to show to you as kind of a diagram. All right. We're going to say item A on the list. We're going to show that item A implies that item A being true implies item J. All right, A was that A is invertible. J was there's a matrix C such that CA equals I. We are then going to show that item J implies item D. And we could actually do some of the things here in different orders. But yeah, we're going to show A implies J. If A is true, it implies J is true. If J is true, it implies D is true. If D is true, it implies C is true. If C is true, we'll show that it implies B is true. This is not a proof right now. This is like an outline of how we're going to prove it. Item C being true implies that item B is true, and we're going to show that item B implies item A. Now, this doesn't cover all of the statements yet. I left some room on the page to finish more of this diagram. But do you see how we get like a closed loop? And actually, once you get a closed loop that means all 5 of these things imply each other. Because whichever one of these things you know is true, let's say you know D is true, you can follow this chain of implications to conclude that A is true, J is true, D is true, C is true, B is true, right? So if you know that one of these is true, you know that they're all true. So actually, we could switch these to if and only if symbols. We could make these double-sided arrows because the closed loop means that any one of these implies the rest. That's pretty cool. That's pretty cool. So we're going to do that. But what about all the other stuff? What about all the other statements? Well, it turns out that we're going to show that D is true if and only if E is true. And that E is true if and only if F is true. So this is kind of like a separate little branch on our diagram. It's not part of the main loop, but it can be done separately. Every one of these arrows is like a proof that we need to do, but it's not going to be as bad as the original idea of doing 121 proofs. We're going to show that item A implies item K. We're going to show that item K implies item G. And we're going to show that item G implies item A. So we get another closed loop here where A, K, and G all imply each other. Because if one of them is true, you can just follow this triangle and get to any of the other 3. And look at this. Look what this does. It means, let's say we know K is true. We could follow the arrows, right? If K is true, that means we know G is true, A is true, J is true, D is true, C is true. You know, so you could get from K to anything else in this diagram. This means that K implies F. This means that F implies G, right? F goes to E, goes to D, goes to C, B, A, K, G. So it's great. We're showing that all these items are true if and only if each other. We've still got a couple more. We're going to show that G is true if and only if H is true, and H is true if and only if I is true. And there's one more missing. Finally, item L is going to be put in here. Item L is true if and only if item A is true. I think that should be everything. So how many arrows did we draw? Because each one of those should kind of be a proof. But, and I guess the ones that are double-sided arrows should be if and only if proofs. So it's still, you know, quite a bit of work, but it's a strategy that kind of makes sense and instead of trying to show every combination of things implies everything. Later in the semester, I said we're going to add some more things to this theorem, so I guess we'll kind of add them into this diagram. All right, let's get started on the proof. And for a lot of these, I'm going to refer you to spots in the textbook or exercises in the textbook. But I think we need to address every one of the arrows that I drew. So proof, item A implies item J because, let's take a look at the handout. So we're saying if A is true, then J is true. So if the matrix is invertible, then we need to show there is an n by n matrix C such that CA equals I. Can you see why J is true? It's because A inverse works. It works for C in J. That's kind of the end of that proof. A implies J. Just let C equal A inverse. So we're done. If A is true, then J is true. Now let's show why does J imply D? Well, This is an exercise in the book. This is by exercise 23 in section 2.1, and I'm going to say to try it on your own. All right, so some of these things will be left as exercises like that. So you could look at J and you could look at D and see if you can start to come up with any ideas. Why does item D imply item C? Well, that is another exercise in the book. This is exercise 23 in section 2.2. And I'm going to say you can try that on your own also. Why does C imply B? We're trying to close that first loop, right? We're trying to do that first loop. So this is true because, all right, take a look at what C says and what B says. C says A has n pivot positions. So suppose A has n pivot positions. By the way, at the beginning of the theorem, it tells us that it's a square matrix. So everything we're saying is for square matrices. We have a square matrix, n by n, it has n pivot positions, and we want to show B, which says A is row equivalent to the n by n identity. So I'm going to say because if A is square and has n pivot positions, then the pivots must lie on the main diagonal. This is kind of like a counting argument, right? You have n rows, you have n pivots, you have n columns, right? So the pivots have to follow this sort of staircase pattern, so they have to make a diagonal, and they lie on the main diagonal. If the pivots are on the main diagonal, then what is the reduced row echelon form going to look like? Remember, every matrix has a reduced row echelon form. I'm going to say in which case the reduced row echelon form is, we know where the pivots are. We know that when we reduce it to reduced row echelon form, we know the pivots will become ones. They will be the leading ones. We know everything above and below each of those ones will be zeros. It's going to be I. So that's why it's true. We need to show, or at least address, why does B imply A? I need to keep flipping back and forth to the handout. B says A is row equivalent to the n by n identity matrix. So if something's row equivalent to the identity matrix, why does that mean that it is invertible? Well, we discussed that a little bit in Theorem 7 in 2.2, the previous video. So some of these parts of Theorem 8 are basically proved as separate theorems in previous sections. So that we closed that loop, by the way. I know we kind of moved the page away, but we closed that loop. A connects J to D to C to B to A. So that's good. So far we have we have this loop A, J, D, C, B, A. Now let's start worrying about some of the other parts, right? And what order do we want to do this in? It's up to us. I'm going to say let's work on A implies K. This is similar to the A implies J. A implies K because A inverse works for D in K. And that kind of comes from the definition of inverse. So I feel like there's not much more to say about that. You could say by the definition of inverse matrix. Why does item K imply item G? Well, that's an exercise. That is by exercise 24 in section 2.1. Just asks you to prove that step. Why does item G imply item A? To close this loop. Well, that's also an exercise. This is by exercise 24 in section 2.2. So exercises are things you can try on your own for practice and to kind of fill in these gaps. Next, I'm going to connect the G if and only if H if and only if I. Let's do all of these together. Let's take a look at what they say. G says the equation AX equals B has at least one solution for each B in Rn. H says the columns of A span Rn. Didn't I say G and H seemed like they were from the same lesson way back when? It was actually from the same theorem in chapter 1. And then I says the linear transformation. All right, so I came from later on, but G and H definitely were discussed together. So this happens by theorem 4 in 1.4. That connects the G and H. That was an if and only if that said that G is true if and only if H is true. But we need, why does I get grouped in with these? It is by theorem 12a in 1.9. So that's when we were talking about linear transformations. All right, we're almost done. Just a couple more things to go. A implies L. A implies L is something that I think I said in the previous lesson, section 2.2. And it was a part of a theorem, in fact. I don't think we proved it, but I guess this is one where you could see the proof of this in the textbook. It's by theorem 6c in 2.2. So we did say it in that lesson. Proof is in the book for that part. How about the other way around? Why does L imply A? This is interesting. So if A transpose is invertible, why does that imply that A must be invertible? Would you believe that this is also by the same theorem? In fact, it's by the same part of the same theorem. It's by this theorem, but with A and AT interchanged, since A transpose transpose equals A. So you basically just look at theorem 6c and apply it to A transpose. You wind up doing the transpose of A transpose. Pretty cool. One more thing to go. One more thing to go. What about this D if and only if E, if and only if F? D, E, and F. Let's take a quick look at what they say. D says the equation AX equals 0 only has the trivial solution. E says the columns of A form a linearly independent set. I feel like D and E being connected relies on the definition of linearly independent. So that's a big part of this, by the definition of linearly independent. F says the linear transformation is 1-to-1. So that would come from that section 1.9 when we had properties of being 1-to-1 and being onto. Okay, so the answer is these connections happen by section 1.7. That's where the definition of linear independence was. And we had some facts about homogeneous systems. And theorem 12b in 1.9. So that theorem 12 in 1.9 had part A was about being onto, and part B was about being one-to-one. Can you see that we did it? We did all of those connections that we had mapped out in that diagram. So I'm going to say this is the end of the proof. And you could say, oh, technically, we didn't really prove it if we left a bunch of things as exercises. But that's where they can be found in the book. Those parts can be worked out on their own. So the invertible matrix theorem is true. Let's talk about it a little bit. We've been talking about it for a while, but let's continue talking about it. So theorem 8. We keep calling it the invertible matrix theorem. We might call it the IMT. All right, if you want to abbreviate it, the IMT connects many ideas together. In a way, a lot of what we've been doing in the course has been building up to this moment to show you that a lot of these things that seemed like separate concepts are actually connected by this theorem. It includes linear transformations, linear independence. I mean, those are things that I might have thought were completely separate from each other until this theorem showed that they are related. Being one-to-one, being onto, the number of pivot positions. That turns out to be important. Like, what if you have a square matrix? What if you have a 3x3 matrix and you know that it has exactly 2 pivot positions? A 3x3 matrix with 2 pivot positions, that would mean that statement C is false. And if statement C is false, all of the other statements are also false for that matrix. And you could conclude all sorts of things about the linear transformation formed by A, whether the columns are linearly independent, whether it's invertible, right? The homogeneous equation, AX equals 0, having solutions. And finally, of course, another concept that is tied in with everything is the inverse of A, whether or not the inverse of A exists. So some of these items on the list are going to be used more than others. I think that items J and K probably are not used that often. By themselves, I mean. If I'm being honest, I don't think J and K are used that much. But look at this diagram. Item J was useful because it helped us prove that A implies D, because we used it as a stepping stone. A implies J, implies D, so J was useful in that sense. Same thing happened with K. We used it as a stepping stone to show why does A imply G? It's because A implies K and K implies G. So sometimes there are statements like that. So which of the statements in this theorem do you think are the most important? I think A is very important. I think C. I think C is a good one, because I think when we do row reduction, we can figure out how many pivot positions a matrix has. So sometimes you can even tell how many pivots there are just by observation. Sometimes you see a matrix, it's already like partially reduced or something, and you can tell how many pivots there are, and then you immediately would say, oh, it has this many pivots, so I can conclude all of these things just from that. All right, so I said remarks, and I only said one thing, so I have another remark. I want to emphasize that the invertible matrix theorem only works for square matrices. Do not try to apply it to any other matrix. Square only. Now, some of the actual pieces, some of the pieces might be true in general for rectangular matrices, but not the whole thing, right? Okay, another note or remark. If we have a linear transformation from R3 to R3, and it is 1-to-1. So let's say I had a linear transformation from R3 to R3, and it's 1-to-1. What can we conclude from that? What do you think? So we know that every linear transformation has a corresponding standard matrix A. In this case, I know that A would be square because it would be 3 by 3. Because the linear transformation is 1-to-1, I could say that item F is satisfied. So all of items A through L are true. That's an example of how you might use this theorem. You have a linear transformation. Maybe for some reason you know it's 1-to-1. Maybe it was given to you that it's 1-to-1. You know it goes from R3 to R3, so it's square. All of the statements in the IMT are true. It means the matrix A is invertible and all the other things. What about if T maps from R3 to R4 is 1-to-1? What can we conclude then? And it is possible. It is possible to have something map from R3 to R4 and have that linear transformation be 1-to-1. Even though the spaces that we're dealing with are different sizes, it could still be 1-to-1. Well, in this case, theorem 8 is inconclusive because the IMT does not say anything about non-square rectangular matrices. A is not square, so we don't know. I mean, pick one of the items, like about how many pivot positions it has, or about whether the columns span Rn or whatever. I mean, some of those things might be true, some of those things might be false. We can't conclude anything directly from the IMT. The IMT is only for square matrices. It doesn't say anything one way or the other for this case. A few more remarks. In particular, I'd like you to notice that F is true if and only if I is true. Now, those two statements, those were not connected directly on our diagram. Let's show you our diagram, our proof strategy diagram. But F, we don't have an arrow connecting them, right? But look at this. If F is true, then that implies E, D, C, B, A, K, G, H, I. So if F is true, then I is true. And vice versa. If I is true, you can follow the chain of connections to say that I does imply F. So it is fair to say F is true if and only if I is true. Let's look at what these statements say. F says that linear transformation is 1-to-1. I says the linear transformation is onto. So does that mean that every 1-to-1 transformation is onto and every onto linear transformation is 1-to-1? That doesn't really seem to agree with what we said back in that section 1.9. It seemed like a linear transformation could be one-to-one or onto or both or neither. But this seems to say one-to-one implies onto implies one-to-one. Let's talk about that. So this means any linear transformation T going from Rn to Rn is one-to-one if and only if it is onto. So what's happening here? What's happening here? Are these just, is that always true then? You know, we would call it a bijection because it has both properties, being one-to-one and onto. Here's the key to it. The key to it is that we are dealing with a square matrix. These are both the same number, Rn to Rn. And that is something that we were not necessarily assuming in section 1.9 when we talked about the definition of one-to-one and the definition of onto. But right now in this section, we are assuming that we're dealing with a square matrix. So we're dealing with a transformation from Rn to Rn. And yes, this is true. If a transformation goes from Rn to Rn, it's one-to-one if and only if it's onto. So they go together, right? If it's one-to-one, it's both. If it's onto, it's both. If it's not one-to-one, it's not onto. If it's not onto, it's not one-to-one. So it's either going to be both or neither, right? For the square case. That's pretty cool. That's something that we didn't really know until now. For square matrices, maybe you might even just kind of think of it in your head as like a square transformation. It's either both of these properties or neither. So that's an interesting result that we get from the IMT. Another equivalent statement. All right, so I told you that, you know how this theorem says the following statements are equivalent and it goes from A through L? And I told you that throughout the semester, we're going to add a few more statements to this list. So we're going to have more statements that are equivalent to all of these. I'm going to tell you one of them now. I'm not going to officially add it to the list yet, but I'm going to just give you a preview of one of the statements we're going to add. The determinant of A is non-zero, where det A is the determinant of A. I guess I didn't really need to say that last part. You know what det A means. This will be discussed in 3.2. As of right now, in this class, as of right now, we only know determinants for the 2x2 case. So we haven't talked about how to find a determinant of a larger matrix yet, but we will. And we will learn how to find the determinant of a 3x3 matrix or a 4x4 matrix, or any square matrix does have a determinant. And at that point, we will say that the determinant being non-zero is equivalent to all those statements A through L. So if the determinant is non-zero, then the matrix is invertible, and it has, you know, n pivot positions and all the other stuff. The columns span Rn. The columns are linearly independent. All of that stuff can come from this, and vice versa. If you know one of those things is true, then you know the determinant is non-zero. That's just a little preview. We'll talk about that in chapter 3. Let's do a little more about how we might use let's say using the IMT. You can call it Theorem 8, or you can call it the IMT. So here's a little example. Is the matrix A invertible? Given, and I'll do this problem for us. You don't have to pause the video or anything. Here's a matrix, and the question is just, is it invertible? So it's just a yes or no question. Now, we learned in the previous video lesson how to find the inverse of A. We could take this matrix and write it side by side with the identity matrix, and then we could do row reduction. We would try to do Gauss-Jordan elimination, where we do full row reduction all the way to reduced row echelon form. It would take a bunch of steps, right? We'd go through all those steps, and we'd figure out whether or not the first three columns become the identity matrix. If they do, then that means yes, it's invertible, and we've found the inverse. If they don't become I, then the matrix was not invertible, but we went through all those steps in order to find out. So how about this? I think the IMT can provide a shortcut. I think the IMT can provide a shortcut. So here's what I'm going to do. I'm going to start doing row reduction on A. I am going to add -3R1 to R2, and I'm going to add 5R1 to R3. Remember, you can do two steps at once, just be careful about it. I guess we're not changing row 1, it's 1, 0, -2, but we are changing rows 2 and 3. Row 2 should become 0, 1, 4, and row 3 should become 0, -1, -1. That's why I chose -3 and 5, was to get zeros in those spots. Notice that I did not put I didn't put I side by side with the matrix. I'm just doing row reduction on A. I'm going to add R2 to R3. So R1 and R2 are staying the same. 1, 0, -2, 0, 1, 4, 0, 0, 3. I didn't fully row reduce it yet. It's not in row reduced echelon form, but I got it into, it's not in RREF, right? It is in row echelon form. It's just not reduced. So this represents a triangular matrix, or represents a triangular system, I guess. All right, here's the idea. How does the IMT help us? We can look at this, and from this, we can tell that there are 3 pivots. The pivots are 1, 1, and 3. This was a 3 by 3 matrix with 3 pivots. So, item C of the IMT is true. Therefore, A through L are all true. So, yes, A is invertible. Isn't that a cool shortcut? I think that's pretty cool. We didn't have to, we had to do some row reduction, but we didn't have to do as much row reduction as we did in the previous lesson, where we set it up side by side with I, and we do full Gauss-Jordan elimination, and you don't really know until the end whether it's invertible or not. Now, of course, the only reason why this strategy worked was because this question was just phrased as a yes or a no question. It didn't really say, what is the inverse of A? If it said find A inverse, then what we did would not be enough, because we didn't actually find A inverse, but we did prove that A inverse must exist. So maybe this is a shortcut for some problems, but not for all. I want to say some more about linear transformations. This is something that can be discussed right here, or it's something that we might have been able to discuss in the previous lesson, but I saved it until now. All right. Let's suppose that we have a transformation from Rn to Rn. Let's let it be a linear transformation. With standard matrix A. We know that it has a standard matrix. I'm just saying we're going to label it as A. If A is invertible, that's still an if, you know? It's not a guarantee. Just because a transformation goes from Rn to Rn, it might be invertible or it might not. But this is going to be something new for us. If A is invertible, then we say T is invertible. Remember, T is not a matrix. T is a linear transformation. It's a rule for how items from Rn get mapped to other items from Rn. But we're now saying that a linear transformation can be considered invertible. And we define... How do you think we're going to define this inverse of T? Well, we're going to write it as T inverse. It's going to go from Rn to Rn. And it's going to be defined so that T inverse of anything that you put in is equal to... Take a moment and think about this. How do you think what do you think we're about to write here? I'll remind you that the linear transformation T, you could say T of x equals AX. T inverse of x is going to equal A inverse of x. That's all. That makes sense. So instead of T of x equals AX, T inverse equals A inverse x. All right, cool. So when a square matrix is invertible, its linear transformation is also said to be invertible, and it operates the way you would expect an inverse to operate. It kind of does the opposite of what T does. Let's do an example problem. Let's move this up. I've been doing all the talking and problem solving today, so I'm going to write a problem and then ask you to try it. So there's going to be 3 parts, so wait until I have written all of them. But let's say you're given T from R2 to R2. And it's defined by T of x equals AX where A is given to you as the matrix 1, 2, 3, 4. 3 parts to this question. First of all, I'm going to ask you to find T of 1, 2. Next, I'm going to ask you to find the matrix A inverse such that T inverse of x equals I should say A inverse x for all x in R2. Part C, find T inverse of 511. Okay, that's the problem. So why don't you pause, take a minute or two, and see what you get for this. Okay, let's start with part A. Part A, this is something we could have done a while ago. You know, this is just a little practice thing about applying a linear transformation to a vector. So this is going to be the matrix 1, 2, 3, 4 times the vector 1, 2. And how do we do a matrix times a vector? I guess you could say that we actually have two different ways of doing this now. We could do it the original way we learned of matrix times vector, or we could do it with the matrix times matrix multiplication that we learned. But I'm going to use that first method. The first method was take the first entry of the vector times the first column of the matrix plus the second entry of the vector times the second column of the matrix. See what this equals. 1 times 1 plus 2 times 2 is 5. 1 times 3 plus 2 times 4 is 11. There's the answer to part A. Part B wants us to find the inverse. So how do we find the inverse of a 2 by 2 matrix? Well, we had a whole lesson about that. A inverse follows this formula, 1 over AD minus BC times the matrix D, negative B, negative C, A. So whatever this equals, where we're looking at the original matrix as having kind of entries A, B, C, D. So let's figure this out. 1 over AD minus BC would be 1 times 4 minus 2 times 3. So 4 minus 6. Right? And then for this matrix, it's like the 1 and the 4 swap places. So we're going to have a 4 and a 1. And the 2 and the 3 stay where they are, but they become negative. We could figure out what this is. 1 over 4 minus 6 is negative 1/2. 4, negative 2, negative 3, 1. And let's put the negative 1/2 in. So the 4 is going to become negative 2. The negative 2 is going to become 1. The negative 3 is going to become positive 3 over 2. And the 1 becomes negative 1/2. And that is the answer to part B. That's A inverse. Part C wants us to find T inverse of 511. Hey, 511 sounds familiar. That's the answer that we got to part A. That's not just a coincidence. You know, I set that up on purpose. To find T inverse, we take A inverse, which we just found. We take A inverse and multiply it by the given vector 511. I'm going to do this the same way I did the other one. I do 5 times the first column plus 11 times the second column. So what do we get? 5 times negative 2 is negative 10. 5 times 3 halves is 15 halves. Plus, up here is 11. And then down here, all right, let's figure this out. 11 times negative 1/2. Let's just write minus 11 halves. Okay. And now let's add those two vectors together to get the result. Negative 10 plus 11 is 1. 15 halves plus negative 11 halves is going to be 4 over 2. 4 over 2 is 2. That's the answer to part C. Is that the answer that we were expecting to find for part C? Yeah, I think this makes sense, right? So check this out. This 1, 2 matrix that we found is the matrix that we had over here. 5, 11 is the matrix that we had here. So I'm just underlining these things to kind of point out to you that this is kind of how we expect an inverse function to work, right? So this is how an inverse linear transformation works. T sends 1, 2 to this. T inverse sends this to 1, 2. So it's doing the opposite of what T did. All right, so that was the problem. Let's see if we can kind of visualize this visually. I like diagrams. I think diagrams can be helpful. So let's say we had, I'm writing a little point here, and I'm saying this point represents some element of Rn, so a column vector. And over here is some dot that represents an element of Rn known as Ax. So, you multiply square matrix times a column vector, you also get a vector. How do you get from X to Ax? Well, the linear transformation T. And the thing that I'm trying to show you now is that T inverse does this. T inverse gets you back to where you started. Practically, you could think of this as up top is multiplication by A, and on the bottom, it's multiplication by A inverse. That's just a little way of visualizing how a linear transformation works and how its inverse works. One thing I want to point out is when I say multiplication by A, really, if we wanted to be thorough, what we should actually be saying here is multiplication on the left by A. The capital A is to the left of this. Same thing down here. Because with matrices, the order matters. A couple of things I want to say before we wrap things up here. By the IMT, Theorem 8, if T is invertible, then T is 1-to-1 and onto. We said that already, right? If a linear transformation is invertible. This is according to the IMT, so I mean for square matrices, right? When I say by the IMT, if T is invertible, we're talking about a square case here. So if T is invertible, then T is 1-to-1 and onto. Well, the new thing that I want to say is, so is T inverse. Because, so I'm saying T inverse is also 1-to-1 and onto. T inverse is also 1-to-1 and onto. Why do you think I'm going to say that's true? How do I know that for sure? The simplest way, I think, to explain it is to say, because it is invertible also. All right, so, and the inverse of the inverse just gets you back where you started. So we've said that an invertible, like a inverse of a matrix, is also invertible. So we're applying that here to linear transformations. One last thing before we wrap up. I'll say also, if you have a square matrix and you know the transformation is 1-to-1, then you get all of this. Like all of this stuff, right? I have a square matrix A and the linear transformation defined by it, AX, is 1-to-1, then I automatically know it's also onto. I know that the linear transformation is invertible. I know that, T inverse exists. I know T inverse is also 1-to-1 and onto. I know that there are n pivot positions. I know all of the things from the IMT. So you don't need to know a lot in order to get a lot. If you know it's square and you know one thing about it, you get a lot of things as a result. Pretty cool. I could have also said if you have a square matrix and you know that the transformation is onto, you also get everything as a result of that, because onto was one of the items in the IMT. All right, so let's finish up here. All right, so that was our lesson. It was called Characterizations of Invertible Matrices. Does that title make sense now? So we could have called this section could have just been called the invertible matrix theorem. That was really the main point of it, was theorem 8. So theorem 8 has 12 statements that are all equivalent to each other. And I told you that, remember, that means they're either all true or they're all false when you're given a square matrix A. For that matrix, the statements could be all false. Anyway, there are 12 of these statements. And I mentioned that throughout the semester, we're going to add some more statements to it. This is going to become a really massive theorem, really powerful for linear algebra. And I'll repeat this again. It is the most important theorem for this course. We have 12 statements right now. I think by the end of the semester, it's going to be 20. I think we're going to have 20 statements all added, not all at once, little by little. And we're going to get to 20 statements that are all either true or false when you're given a square matrix. They involve the determinant, and they involve some concepts that we haven't even gotten to. Excuse me. So that's a good place to stop. And as always, I hope everybody is doing well, and I'll see you soon. Take care.